What's up, everybody? Welcome back. Today we are working on our virtualized GPU, and today's topic is trying to get perspective-corrected triangle interpolation. So, what am I talking about? We are working on this GPU. We have extended a virtual machine, QEMU, with our own PCI device, and we've written a kernel driver and an OpenGL driver to go with this thing. Which means that we can run a typical OpenGL program and attempt to display something reasonable. So if we have something like a program that uses a vertex shader that takes in a position and a color and spits out basically that position with four-dimensional coordinates, or homogeneous coordinates, I guess is probably the better word for this, and passes a color to the fragment shader, and a fragment shader that just outputs that color. This should allow us to this is the world's simplest OpenGL program, right? If we run our application, we see some amount of success here. Hold on, it's really slow right now because I'm spamming some prints from yesterday that I didn't clean up. But we have a triangle that shows on the screen, and we can see that it is interpolating blue, green, red over here. So that's pretty cool. It crashes as well because I don't know. We didn't really we didn't really get to the end of this yesterday. But the problem with what we did yesterday is that the interpolation of those colors does not take perspective into account. So I think the easiest way to show this is going to be to open up Blender. And let's just kind of show you what I'm talking about. So let's say that you have a triangle, right? So let's make a plane, and we will kind of cut this thing in half and then delete one of these vertices. And we have a triangle here. And let's maybe set the kind of make it what's this called? Isosceles. And let's say that this triangle is supposed to simulate a long hallway, right? So if we stretch this vertex way back here, and maybe if we rotate this thing around the x-axis, because the camera can only kind of sit at a certain angle, right? You could kind of imagine this is a wall in a long hallway, right? And let's say that the wall has this wallpaper on it, right? And the wallpaper is going to just be basically vertical stripes. So let's just quickly slam something that looks like that. So if we go I think we want the texture coordinate of this thing, or maybe we want the object coordinate of this thing. Yeah, we feed this into a sine wave. I think we need to separate x, y, z, and then let's stick, I think looks like the x-axis into a sine wave, and then kind of slap that into the color. There we go. We have some stripies, and then let's try to scale this a little bit so that the stripes look a little bit more reasonable. Math. Can we just multiply this and kind of ooh, okay. So we have stripes on a wall, right? And what you'll notice here is that as we go into if we look at it straight on, all of these stripes are the same size, right? In terms of where they are on the screen. But if you look at this, as you go farther and farther away, the stripes get thinner and thinner and thinner, even though they are the same width really everywhere, right? And the reason for this is because things get smaller as they go farther away from the camera. Wow, genius, right? It's crazy. Now, where this gets tricky is this calculation is actually done after projection, right? So what do I mean by projection? Okay, so you view the world, you can imagine that you view the world through a camera. How do you draw a camera? They kind of look like this or something, right? You see the world through the camera. And the camera kind of looks at the world as if there's some it's seeing an angle of view, right? When you look far ahead in the world, you can see more of the world that's farther away in terms of distance than things that are close up. Right? So at each slice of this, you're seeing farther and farther and farther and farther as you go out, right? But we're capturing this on a 2D surface, right? So what you can imagine, kind of, right, is the typical model for this is you use pinhole camera. So stuff goes like this, and then you draw kind of the backside here, and you can kind of imagine that if you send all light through this infinitesimally small hole, basically you're going to get an upside down reflection of the image here if you had a photosensitive piece of paper, right? We're using that same model. So you're going you have all this stuff in the world, and you're trying to kind of flatten it onto a 2D surface, right? And so the way you do that is you basically can determine hand wavy. We'll get into the details a little bit more later, but things that are farther away look smaller. But basically, you're just taking like at each point in here, if you look at like the thing that you can see, you kind of like put that on the sensor as like a ratio between like how far you can see and how far it is. And so the reason that's a problem is if we were to just kind of do interpolation on these three vertices, after projection, they're kind of like on a flat surface. And so what you would really get is something that's like more like this, right? Where the width of these things is constant. Actually, hold on, window. I think I want window. Does that look better? Hold on. Maybe if I move the camera has to be where we are. So can I do like something that's like, view, lock camera to viewport, and then bring it around, right? So this is what you would see if we didn't do that versus this, right? Where things get smaller and smaller. So this is kind of what we have right now in our implementation, where we're interpolating these things as if they're flat, but in reality you have to interpolate them as if they're getting farther and farther away. So that's the goal for today, is try to like make this test case work for our triangle interpolation. So I think the plan of action is approximately create a test case in OpenGL land. When we create that test case, surely our program is going to fall over because our shader won't compile correctly. Because like we haven't implemented things like sign X inside of our fragment shader. So we're gonna have to figure out what's gonna crash, fix that. Then we have to update our code a little bit. I lied a little bit earlier when I showed that like colored triangle. We kind of hard coded the vertices on that triangle to be red, green, and blue instead of using the actual output of the shader, the fragment shader. That should be easy to fix though. And then we should actually implement the correct answer. And so that's the plan. And let's just kind of see what happens. Let's see what happens. So in order to reduce the amount of fixing that we have to do, I want to pre-compute a triangle that is like perspectively like that looks like this, because our shaders don't have matrix multiplication implemented yet. I'm sure that's not that hard, but that's not what I want to focus on today. So I think we can pre-compute this. And the way we do that is, let's look at the graphics pipeline on Wikipedia. Basically, you send all of the vertices that you want to use through this like projection matrix, which basically does the math of saying like, of this here, right? We're like things farther, smaller. That's essentially what this does, right? Because in OpenGL world, everything kind of shows up in like this like cube, kind of, right? Everything's in a cube. And so things at the front of the cube, you draw a triangle here, that looks kind of like the same as if you drew a triangle on the back of the cube. There's no perspective applied to this thing. And so the way you actually get perspective in OpenGL world is you actually just make the triangle at the back of the screen smaller. Right? And so what you do is you warp the whole world to fit in this box, and things that, and like you kind of like take a view of the world that looks like this, right? Things farther away are fatter, and you just kind of like squish this in so that it looks like this, right? So you just kind of have to like reduce everything. And so that's what this projection matrix does, is if you take vertices and you multiply them by this thing, you get basically this. Now, I think for me to understand the projection, why perspective adjusted interpolation works, I think deriving this matrix will help with intuition a lot. That's the only way that I could get to like the right answer when I was like looking at this yesterday. So I think it's important to try this. So imagine we are looking top down. Here is like the stuff that we want to see in our camera, right? And let's say we want to kind of make this box, right? How do you determine which pixel on the screen should be set by this if you have like a thing right here? Well, you can do a little bit. We know that like we want to see the ratio of like the dot. So we want to see the ratio of this distance over this distance. Well, at that point, right? So if we draw like a line here, we want to see the ratio of that dot over this distance, if we're looking for this point here, right? And so what you can do is you can take like its initial x position. So if this is if the camera's at like 0 x, right? 0x. This point is going to be at like negative something x, right? He's going to be off to the left a little bit. And this point is going to be negative bx, right? Some point that's farther. And so we want to find like a over b essentially, right? Maybe like negative a over b. We probably want like the magnitude of b, but the direction of a preserved, right? Hand wavy. So you can calculate this pretty easily, right? If you have this value, which we do, then this is just like a little bit of like simple trig, right? So you have like this angle is going to be like theta, your angle of view. This is just going to be what? B is just calculated by opposite over adjacent. So you have adjacent, which is z, and you can just calculate this as what? Tan theta over 2 is equal to b over z in this scenario. So the width of this section is just you multiply it over, so z tan theta over 2. And since we want the ratio of like a over this, we have like a is equal to, or like the new value of x is going to equal the projected value of x, which I think people use, they put a little prime on here, is going to be like the value that it previously was, so we call that a, over the total width, so z tan theta over 2, right? Now, here's where things get a little interesting. In order to get this value, we have to basically like tan theta is like a constant, right? We're going to have that same value used everywhere. And what we want to do is we want to like encode this in this like projection matrix, right? When if we're trying to get to like this box, we have to understand what this box represents. But this is like a very, very powerful matrix. How do we explain this? So, you know, your typical matrix math, you have like a box of numbers and like maybe like a box of other numbers, and we could put our x, y, and z position in this box, right? And when you multiply this matrix, you basically have like, if you have like 1, 2, 3, 4, 5, 6, 7, 8, 9, the way you like compute the answer to this like multiplication is you kind of do like, you multiply each thing in a row by each thing in this column. So you take the x here, the y here, and the z here. So like this is going to turn into like x plus 2y plus 3z as like the new x value. Then like 4x plus 5y plus 6z, and 7x plus 8y plus 9z, right? That's like kind of like the new output for this. And so this is like mathematically easy to compute on a GPU. These like matrix multiplications are like very easy. But what you notice about this is that there is no way to do like x over z, right? You can only multiply constants by the input values, right? That if this matrix is like a constant thing. And so what they did is they introduced this concept of like this thing called like a homogeneous coordinate. So if we were trying to represent this, where we have like essentially constant times 1 over z, you need to be able to divide by an element in here. And so they add like this new element called like the homogeneous coordinate, w. And that w is like the world representation of this thing is x over w, y over w, and z over w. You have this like extra thing, and it acts as like a divisor. So if you want to represent this, you can say, well, we need a box. Let's fill in like elements of a box that will do what we want here. So can I fucking expand this down? So we want like a box of numbers so that if we were to multiply x, y, z, and 1, we would get like this output, right? So we want to multiply x by something to get a new x. So we know it has to go kind of like over here so that x times that thing shows up. So we can do, this is like 1 over tan theta over 2, right? This gets you kind of like this part of the equation. And now you just need like a divide by z. So what the trick here is that since this last element is like a divisor, you can put 1 down here, and it means that you'll get like your 1 over tan theta here, right? Then we'll get like some other stuff. And then down here, since you have like x, y, z, w multiplied by this stuff, if you fill in zeros here, the new value of this will be z, right? And so when you apply that like homogeneous coordinate mapping, you now have this over this, which gives you that, right? Big win for us, big win for us. So that kind of fills in this top left corner. Like we just do the same thing for the y-axis because we're doing this in like multiple dimensions. And that's what like this -1 here is doing. Their matrix is flipped from mine because I always think of it as like row major. They're thinking of it as like column major. Whatever. It doesn't really matter. Doesn't really matter. Now they have these other two things in here that are a little confusing. What are these for? So in this picture, maybe we draw it again. We have the x and y stuff sorted out, but don't forget that we also have to map z, right? So if we're trying to fit everything into this box and our camera's over here, we kind of want to say that like this is 0 and this is 1, right? You kind of want to like map all depth ranges in the values in the range of 0 to 1 so that you can like output this depth to a texture, right? When you do like OpenGL rendering, something that they will often do is they will create an image that maps the depth of each pixel to something, and this 0 to 1 mapping is like very convenient for that. I don't know what you're trying to represent here, but I like the thought. The thought is like you're like, if this thing, then 1, else 0. Perfect. Okay, so what we would normally want to do here is you would want to have like a linear mapping, right? So you just take the z value, and if we call like this near and this far, you kind of want to say that like, okay, if we want near to be 0, you do like z minus n. We'll make it so that at n we're 0, right? You plug in n here, n minus n, 0, right? Then if you want like this to be 1, you divide that whole thing by the distance between these, right? Far minus near will get you like the ratio from 0 to 1. Now, the problem here is we have put z in this this homogeneous coordinate here, right? So when we're actually, if we tried to like plug this in, we would have a problem because you can't represent this. How do I say this? Since this whole thing is going to be divided by z at the end, you need to multiply this whole thing by z to offset it, right? Maybe it's easier to show this like if we like pull open a Python shell. Let's see. Let's see. I think it's easier to show it this way. So if we go like def interp z or something, right? So we're gonna take in like a z value and try to return a new z value, right? If we want like near is equal to 0, far is equal to 1, we do that same formula where we have like z minus n over f minus n, right? And then we do print interp z with near and far, right? Let's just start there. So if we do this, we have 0 and 1. Wonderful, 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 right? Now, the problem here shows up when we want to divide this thing by z later. I guess we'll do z is equal to n, z is equal to f here. And then we'll use z like this. Boom. He doesn't like that. Why? Is it because I've division by 0? Oh, oops. Let's do 1 and 4. That way it won't happen. Okay. So now if we divide by z, we have like a problem, right? It's no longer 0 to 1. If we don't divide by z, we're chilling. Right? Simple. 0, 1. Now, to offset this, you can multiply this whole thing by z, and we're chilling. We're back to 0 to 1, right? Because you just undo the operation that you're doing. The problem is, this now requires like a z squared, right? Z times z. But you cannot represent z squared with constant times z. It's impossible, right? You would have to like do another multiplication here or something. I'm not really sure, but it's not representable in this matrix. And so the trick here is you only care about the 1.0 and 0.0 cases, right? 0.0 already covered here. But the 1.0, you can just swap this z for an f, for an f, the distance at like the far side. And now all of a sudden this starts working again, right? 0 to 1. But this is no longer a linear function, right? If we take this and we like plug it into Wolfram alpha to graph it, Wolfram alpha, if we say like, graph this, we do f of z here, where f is equal to 4.0, n is equal to 1.0 from what n to f. Is that gonna work? No. Let's see if does it graph this. Okay, and then we go from z is equal to 1 to z is equal to 4. Does it do that? Yeah, okay. This is linear, my bad, except this over z, which is what we're actually doing, is not. Aha, yeah, so this is nonlinear. And this is why the like perspective work, why this is a problem to begin with. That's why this happens. But we have, I think, successfully derived the other elements of the projection matrix. Right, they have 1.0 over near minus far, which is the, where are we? 1.0, oh, they have everything flipped. They have a negative near minus far instead of far minus near, but it's like the same shit. It's just inverted. So they have, I think that you can rewrite this as f times z over f minus n. Yep, minus fn over f minus n. Yeah, if you expand out this, you end up with that. And so you take like the two terms, one is multiplied by z, other one not, you end up with this 1 point over near minus, oh, sorry, it's this one. Far over near minus far, near times far over near minus far. That's the same thing that we got here. And then, yeah, that's it. We have like we have created, we have re-derived this projection matrix, which is great for us. So this is what people would do for real in like normal game code, but we will do this, like most people would put this into their vertex shader and have the GPU compute this for us. We cannot do that right now because our vertex shader does not support this thing. So we'll just kind of like write it by hand and figure it out from there. Introducing far and near plane is completely unnecessary. All it is that you were interpolating with proximity as the interpolant rather than depth. Far and near are purely for wrangling your proximity value in OpenGL to -1 to 1 range. That's not unnecessary though, right? If we are going to be using this matrix to generate values that OpenGL is going to render, we have to do that same thing, right? Okay. So let's maybe import NumPy in Python so that I don't have to think about any matrix math, and we can just kind of, you can use 0 to 1 naturally. True, except I need to make sure, I'm trying to make sure that we end up with the non-linear mapping. That's like a very important part of this like perspective problem, is that the shape of this output needs to match. So you could do you could do near and far as 0 and 1, except you would still need to do something where you end up with like this 1 over z shape, or else we wouldn't be able to test the failure. Anyways, let's shove a matrix in here. So, how do we want to do this? We have mat is equal to, I think you can just do it like this, where we have like a two-dimensional matrix, and we can do like, we do like field of view is equal to like 90 or something. And then in here, we'll do something that's like, let's see. We'll call W is going to be 1 over math tan f of e, except this has to be in degrees, probably. Or radians, I mean. So I think it's probably like this. We'll call this W000. This probably needs commas, almost certainly. We'll replace this with 8 with W again here. And then we need a -1 here. Because they want the typical projection matrix is inverted. I think it's because OpenGL uses negative Z and Z differently than I was thinking of them. And then we'll call this like clip Z clip. Sure, that's fine. Is equal to F over N minus F, and Z clip 2. We'll call this F times N over N minus F. Okay, which means that we can put Z clip here and Z clip 2 here. Okay. This stuff needs to come up like this. And then we should be able to go like print. We take like a triangle and we take like vertices that we made like in OpenGL land. We want to make sure that our axes are right. So in our world, in OpenGL land, we have X and Y is vertical, and then Z is kind of like into the distance. So let's rotate this like this, and then like this. And that should give us some points we can start working with. So can we apply all transforms, take this. So we have y1, z1, x0. So we'll call this vertices. So we have 0, 1, 1. Simple. We have 0, -1, 1. Makes sense. And then we have something that's like probably like deep as fucking Z, right? So we have sure, it doesn't really matter. We have like 0, 0, 30-ish. I'm not sure if this is be positive or negative. We'll kind of figure that out later. And then can we kind of move these a little bit to the left? I've seen your comment. I don't like. I'm not. Like. Don't tell me what to do. don't tell me what to do. I'm gonna do it this way because this is the way that makes sense to me, and it's fine. I also think that yeah, it's fine. It's fine. This is just gonna be. This works. So then we can do something that's like for vertex and vertices. We can do like, doesn't matter what makes sense to you, matters what was right. They're the fucking same. Shut the fuck up. Okay, so we're gonna do like, we're gonna need to like numpy matrix turn the matrix into a numpy matrix. Which I know I don't remember how to do this. I think it's like numpy array. I think is what I want. What's right is right. They're both right. Okay, I'm just gonna click ban you. Shut the fuck up. Okay. Okay, so this thing we need to take in the matrix. So then we do like mat times vertex. And I think this should give us something reasonable. We can take a little guess and see if this is right. Maths. That's right. That's right, Mug. We are doing maths. Okay. No module name numpy. That makes sense. Nick shell Python 3 packages numpy. And run it. Okay. Not quite. So import operands have mismatch in core dimension. That's true because we forgot that when we are doing this matrix multiplication, we need to put a 1 on the end of each vertex because homogeneous coordinates. Okay, and now the question is do these make sense to us? So we have, I think that our near and far plane need to be a little bit fatter. So our far plane needs to go, okay, so we did keep these things, each of our initial vertices at 1. So we're going 1 to 30. Let's just give it a little bit of extra room. So we'll go from 0.85 to like 35 or something. Does this make sense? Does this make sense? So every vertex is on 0 in x, which is a pain in our ass. It does kind of seem like we should move these things over to the left a little bit. That seems reasonable to me. Okay, and then these are like very slightly to the left. We're gonna have to think about this a small amount. So maybe we should set camera parameters that are like sane for what we want. So let's take our camera here and just try to set like a reasonable field of view. Lock camera to viewport, so we kind of like move this thing up like this. We kind of want to see something that looks approximately like this. So we have the camera position is like where? I don't want to lock this thing anymore. Please unlock. There we go. Okay, so the camera is like, in this scenario, the camera is 8 meters in the air, 8 meters back. So all of this stuff needs to go forward by like, 8 approximately. We're not really thinking too hard about this. And what's his like field of view? Can we go to there's like lens here, focal length 30. Can we do this in field of view? So this is like 40 degrees. Okay. So that seems pretty reasonable. We have, well, the same x value on all of these. I'm not really convinced that makes sense. Oh, it does, because it's that the last one is divided by more. Right, so we have -5 over -38 versus -5 over -8. We are chilling. Okay. Why are you doing double FOV instead of half? We should be doing half FOV. That makes a little more sense. And then can we punch these numbers into our little test application and see if they're reasonable? If they're not, we probably got some negatives wrong. Can we look up like OpenGL Z direction? Is it like, is it supposed like default negative goes into the world or positive goes into the world? Clip view space, camera projection, blah blah blah, clip space. Can we look up like default depth test OpenGL? Blah, 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 blah. what's like the default value here? Can we just look up like GL depth func here? Negative goes into the world. What a weird fucking default. I guess that means that uh you might have like more precision at things closer to 1, which might be helpful in some version, some way, shape, or form. Which means that like this makes sense because this is backwards from what we would have guessed if we had positive goes into the world. Okay, sure. So this makes sense. So this will be on the screen, right? We have -1 over -8, so that will be like less than 1 to the left. This will be less than 1 to the left, and this will be way less than 1 to the left. Perfect. And this thing is much deeper in the screen than this, which makes sense again. If we do this over this, we end up with a value greater than 1, which doesn't really make sense to me. So is our near plane too close or something? Because it seems like we're supposed to be going near plane. Is it these have to be negative or something? Yeah, it does. Okay. Yeah, okay. So this is going to be some value between 0 and 1, right? -3 over -8. And this is going to be some value less than 1 as well, -37 over -38. So I think we're chilling. These look like 3 reasonable vertices. And so if we go into our test app, which maybe we'll do that here, hopefully we can construct something that looks approximately like what we asked for. We'll test this first in like our with like an existing GPU, not ours, because our GPU is broken as fuck. So let's look at vertices here. Vertices. Where do we construct this? Here. Okay. So before we were giving like a triangle with 3D coordinates plus a color. I think that we want to give like a very similar thing here. But we just want to like update these to pass in the 4-dimensional coordinates as well. Because that way we don't have to implement anything that is not currently implemented in our vertex shader. So I think we can do like this, throw some commas in here, like this. How do we do this? We go to the end of word, comma, next word. Okay, there we go. Okay, then I think that Zig is probably angry that we don't have like .os here. And then we also need to like preserve the colors. So the colors go here. Okay. And now we have theoretically something that might work. We need to update this thing to say that our first input to the vertex shader is going to be 4 elements, and these things are going to be 7 elements apart instead of 6 because we've added 1, which means that this thing is going to be off by 16 instead of 12 bytes. And we have to update our vertex shader to take in 4 inputs, and he can just say the output is directly what we input. So I think we are chilling there. This, I think, might work. We will see. So let's build this thing. We'll start up our virtual machine. I think we can do it actually from this directory now. I think we fixed that little bug. Although he does want GDB, which is a little annoying, but can we just turn that off? Okay. Okay, so we should be able to then transfer the new version of our app over to the thing, and we should be able to see something that looks kind of like a triangle going into the middle of the world here, but we aren't. So we've done something terribly wrong. We have done something wrong, which is a little annoying. Let's quickly just try inverting a negative here, just to see if that's related in any way, shape, or form. He's mad because we have to kill the old version of this. Oopsies. We do need to log in before we do anything. That's true. Okay, so now we run this and... Okay, so that's looking a little bit better, for sure. There's a little bit of a problem here where the real GPU, we don't have like the coordinate system set up right, so it's a little bit down to the right, but this is what we wanted. This is what we wanted. And then let's set up a little fragment shader that will, instead of taking in like the color here directly, can we take in like UV coordinates essentially? So maybe we will take in just like the X position of the wall or the Z position of the wall, kind of like from 0 to 1 or something. Or we could just pass the Z coordinate over. We could get away with either. Let's for now just say that the things that are close to the camera have a value of 0, and the thing that is far from the camera has a value of 1. That's the easiest for me to work with. Which means that this thing is going to be 1 float. And we are no longer 7 offset, we are 5 because we've removed 2 elements here. Our vertex shader is now going to say that our input here is going to be a float. And we are going to output a float as well. Frag x pause. We're just going to go frag x pause equal x pause. Boom. And then in our fragment shader, we should be able to go like, we have a frag x pause, and we want to do something where we just have like float val is equal to sign frag x pause maybe times 100 or something. I don't know. We'll figure it out. And the colors is going to be val 1.0. I'm not like 100% sure this is right, but we can play with it until it works. So there we go. That looks right? So we have some sort of stripy lines that get farther and farther, like kind of closer and closer and closer as they get farther and farther into the screen. I'm sorry, man, I'm not a troll. It's okay. Whether you're a troll or whether you're just like a little misinformed about what is expected around here, either way, it's my chat and I can get you to shut the fuck up. The swizzled result should be f times x, f times y, negative near, negative z. Yeah, that's... I'm not 100% sure that's correct. I'd have to think about it. I think you're missing a near like you're missing this stuff. If you use infinite far plane. Oh yeah, sure, because infinite far plane becomes, this essentially goes to 1, and this essentially goes to infinity, and then we get it divided by infinity is approximately 0. Whatever, it's fine. It's fine. Okay, never mind. You are a troll, and you're banned. Fuck off. Go away. All right. Okay. So we have a little test case, and we can try to run this now on our GPU and just kind of see where it falls over, because it will fall over. So if we run test app dev dri card 1 now instead of card 0, I guess we can say that we've created the test case and we're on to trying to fix shader compilation. We can do ner debug is equal to print vs. So this will tell us what the OpenGL compiler or the GLSL compiler kind of hand wavy is going to give to us, and maybe we want like print fs as well. And so we can see that we crash on something, but here is like the program that we are going to try to run. So this is the vertex shader. Do we not get the fragment shader anywhere? Oh, here's like a fragment shader. So here they have a load of a constant value 1.0. They take the input value, frag x pause, like we just wrote. He tries to use those things, and then he says fmol this times 100, right? Because we did thing times 100. He says fsign thing, fsign this thing that we made, and then we try to put the output of that thing %7 into the output. So presumably we're just gonna, it's probably just mad that we haven't implemented the instructions for fsign and fmol, as well as probably we haven't implemented the piping of floating point values between the fragment and vertex shader. So we can fix that. Let's see. We'll start here. Yeah. So the first thing he's mad at, he's like, hey, he being us. This is the code we wrote. He's saying, yo, we only support passing like vector 3s or vector 4s between the vertex and fragment shader. So that's easy to fix. Easy to fix for sure. So we'll go into Mesa. And I guess when we see, what line is that at? That's at line 243. We can just switch here on the number of vector elements, which we do here for sure. But anywhere that says output here, we should say input. And we don't have to support, we do have to support both vec4s as an input now, as well as floats. So we need to implement these functions in our GPU implementation. So I guess we can do that really quick too. Maybe I want like a second window here. Oopsies. Yeah, let's do that. Let's make a second window. So can we go to libgpu, and we have like this header file that says, hey, we want to set some inputs, please. So we put a vec4, we put float, and we have to implement these things, of course. So we're going to take these, and we're going to go into our shader, C bindings, and I guess we're going to look for push input here, and we'll just kind of implement the things that we're missing. So pub, export, function, this thing. He takes in a shader that's a shader builder and returns a bool. And this is going to look almost identical to the vec3, except we're going to type vec4. And then we're going to do the same thing here, but with float. I think everything else should just work. He's going to say F32 here. Okay. We build our libgpu. Can you write a library in Zig and generate C headers from the export signature? I believe so, except that's just way more work, so I'm not going to do it that way. I don't mind writing the header on the fly. What I do like to do, though, is I like to check, you can like in Zig, write like a comp time assert that will check that the function signatures of what you wrote are the same, and I find that a little easier, because it's like, I'm kind of like doing a couple hacks here. I'm doing what like I like to call link time casting, right? So I define here that there's like a struct libgpu. And this thing doesn't like actually exist, right? But like in normal C, you would implement this struct in like the implementation file, and then your APIs would take in that thing. I just like cheat and say, well, he's gonna pass in a fucking pointer, so I'll just make that pointer like a Zig type here, and then like not think about it. I mean, generating headers for consumption for C users, but the library is written in Zig. That's exactly what I'm doing right now. But I'm just not doing the auto generation because I don't want to have to like codify the hacks. I just find it easier to just do it myself. It's not worth the automation in my eyes. Okay. So this was built, which means that this should build as well now. Mesa with like the new input bindings, and can we copy the new version over and just see where it crashes now? Because he's likely going to crash as well. Okay, so now he is mad at 243 again. Wow, that's a little surprising. Oh, right, because we left the assertion in like dumbasses. That would do it. That would do it. We do need to delete the assertion. What's the library you're building? It's an implementation of a GPU in software that processes input commands and runs them, as well as compiles shaders. So we're linking to this library in Mesa so that we can do like shader compilation, and then we are linking to this library, a slightly different library in slightly different library in QEMU that will actually execute the shader. Zig has f emit h and a C backend, but as far as I know, both are incomplete. I also don't like that when you use that like f emit h, it kind of includes like a Zig header and that will allow like kind of allows for a bunch of like Zig types to be used in the headers automatically. And I don't want that because like I want to use the C header types. Okay, the unhandled number of vector output elements at 262 is the next thing to fix. So this is the same problem, except we have to do I think this is probably like a floating point output. So we need to codify that. So we just change vec4 here to float and write f32 here as well. Go into our header binding, our shader compilation stuff, and we add an output for float. And I think that fixes this. I think. Okay. Now, I guess we didn't fix some assertion somewhere. So this is at assertion at 282. This is saying like in the fragment shader, we have like the same problem. Yeah, and we have this like fix me in there where we're like, this is just like the fucking same as the vertex shader version. And it's like, yep, it sure is. But instead of addressing it, what if we just didn't address it and just copy pasted some code? What if we did that? Wouldn't that be cool? All right, give him a sec. Run it again. And we're at assertion at 491. He's mad that the source format is not an RGB float. That's true because our source format is probably now a single element float, not a 3-dimensional float. That makes sense. So, and that makes sense here because we're saying that our, so this is like kind of the how do I say this? We pass in data to a fragment shader. Maybe I should keep this around. That seems like maybe relevant. We pass data to a fragment shader or a vertex shader by basically like taking a buffer of numbers, right? 0 0.5, 0.5, 1.0, right? And we kind of say like, hey, we have like definitions for these things. So the first 3 elements of these are going to be like X, Y, Z. They're going to be like offset by like this amount of space. And we're going to have like another thing over here that's like RGB or something, right? So we basically pass this buffer over to the kernel and then over to the GPU. And then the GPU needs to know like how to interpret that data. So that's kind of like what's going on here is we're saying like, yo, here's a definition of something. Now, I think we can just do this. So we switch on the format. If the format was this thing, we do whatever we were doing before. And then presumably there's one for kind of just R32 float. Presumably this is the one that we're going to be hitting now when we have a single floating point value. And we just need to say like, yo, could you push a definition for a float? Which means that we need to do the same little hack, or not hack, just the same update here where we have input defs push vec3, we put push float. And then in our C bindings, we have defs push vec3. We do the same thing here where we push a float. And once again, we just have to change the type here. Should be fine. Should be fine. He's mad because it doesn't exist. Did I not save the header? I did not. Okay. So we compile. And now he's mad because we just left an assertion in there. We did just leave that assertion in here. And then we also probably have to do like default assert unhandled vertex attribute format, we'll call it. Okay. Let's see. All right. We do still have an unhandled vertex attribute format, so let's maybe print what this is. Because I clearly don't understand. So we'll do kind of like this. Thank God the test is easy to run, or else we'd have to bust out the debugger and like actually use our brains a little bit. But so this is number 16. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, because not only is there like the single value one, there's also the 4 value one. Right, I forgot. So we have another one. Another one. So this is a vec4, which means that we need vec4, which means that we need vec4 here. Is it possible to test this in Nix without having to go through QEMU? Well, the problem is the fact that we are using a virtualized PCI device. We could probably do this whole, we could probably create like a full software loop where you kind of force Mesa to use like a custom software rasterizer and then skip like then you could like bypass the kernel and PCI device probably. But I think what I'm going to end up doing is I'm going to basically make it so that shader execution can be recorded. And then I'll just make an app that replays shaders. Because I think that's where most of the work will end up being later. I just haven't done that yet. But it's not the end of the world. I don't really mind doing it this way for now. If we were restarting the virtual machine a lot, it would be a lot more painful. But I don't really mind this like copy the thing over. Okay. So we are now making it to where the shader has been fully uploaded to the GPU. But we are getting errors when we try to when we are trying to like parse this thing. So that's going to be on the other side of the GPU. QEMU is now like interpreting this shader. We have this things like unimplemented input parser. So where is this coming from? Extract inputs from buffer. Yeah, this makes sense. So I guess we have to handle vec4, which probably uses the same start and end inputs, right? Because these, but the end, ooh, input end is probably type dependent. It looks like just kind of hand wavy. So maybe here, if we're doing a vec4, we're going to use size of vec4, 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 and for floats, we're going to do something similar. So there's going to be size of float, f32, and there's going to be f32 as well. Now, if we get a floating f32 output, we're not interpreting this thing as a bunch of floats, but we're interpreting this thing as one float. So can we do like bytes? This is still going to, I guess this was one vec3 as well. So I think this is true. This is fine. Okay, so now we have to recompile QEMU to pull in the latest and greatest of our lib GPU, which means we have to go into the QEMU environment, which is a little bit of a pain in the ass, but whatever. And this is where it would be nice to be able to test lib GPU directly, but you know, whatever. All right, compile, run. Wait 10 seconds for it to fucking boot the virtual machine after linking. We are actually already running the virtual machine, so let's close it and open it again. And let's give it a sec to boot up. And let's see what happens. This feels wrong. Invalid reference. Yeah, okay. So there's more shader compilation that needs to happen. But we somehow managed to dodge it, probably because we're missing an assertion, which is bad. Because we had those new instructions, fmul and fsign. Those are not implemented. So I don't know why, like, someone should be mad about that, and they're not. So we need to add an assertion and then fix them. So go to source, Mesa. Okay. Somewhere in here, he has like mathematical operations. I would assume it's here. Do we have like unhandled ALU op somewhere? No. Is there like an assertion? We have an assertion here. We have an assert unhandled type. Instruction deref, intrinsic, load const. I guess it could be like an intrinsic. It's not an intrinsic. The intrinsics are printed with an at sign in front of them. Oh, here, unhandled ALU op fmol f sign. Here we go. That's what we're looking for. That's what we're looking for. So we're in this case, and this should be a assert. So if we do this now, we should crash again, which would be wonderful for us. Boom! Crashy, crashy. And we just have to implement this. So we need, we have, what was it, F sign? We have F sign and F mol. Okay. Let's see what the fuck is going on here. So presumably we're gonna do something similar to this where we push a command. We're gonna push a command, and we're gonna have to like take in some arguments to that command that we're gonna have to figure out where they come from. So maybe we look at the NIR print again. This is kind of where this NIR is like the Mesa intermediate representation of this thing, basically what we're seeing printed here. And we can look for like where he talks about fmol here, and we can use those to figure out how we're supposed to inspect the arguments of this operation, right? So we can look for like the word like fmol, right? Oh, he's probably doing ALU op. Yeah, we probably have like, since fmol isn't in here, we probably can just follow the same thing that we're doing here. So they have like, can we look for like NIR ALU instruction here? So this is how they print a ALU source, and then this is from print ALU instruction, right? So they're saying that this thing is equal to this thing, right? Then we see %2, %48. So that's probably this. Print ALU source. Okay. Yeah, it seems reasonable. So our move 4 is probably doing the same thing, right? Source SSA index. And then here we're extracting a channel. I think that there is no channel to extract from here, which is good. So we should just be able to do like, we're gonna do fmol. And the fmol is gonna take in 2 arguments, which are going to be kind of like 2 other variables that we've already extracted. So it should just kind of be like this, I think. That would be my guess. So we multiply a by b. Oops, this is the wrong one. And then for f sign, we only have to take in one thing. And that should work. That should work, which means that our implementation of this thing, we need to add some commands that we can execute. So our command here, we're gonna add f sign, which is a struct. And his input is going to be a, I guess, index. And we're gonna have fmol, which is gonna have a and b. Right, we have to assume that that's reasonable. And these are gonna be indexes as well. Because everything operates on like another variable, not on like the thing, not on the values directly. So what's gonna happen here is like, they're gonna load a value into variable 2, and then load a value into variable 48, and then multiply those 2 things together. So we can do things that way too. So here we're like, yo, we have an fmol to deal with. And we can just say, oh, it needs an output as well, huh? These things need to get stored somewhere. Surely. Surely things need to get stored somewhere. So we also need an output value. Okay. So then we can do SSA's put with our allocator, where SSA is basically like our variable list. We're going to put those in the output. And the output is going to be, I guess, a float that is equal to f dot a times f dot b. That seems reasonable to me. And sign is going to be very similar, except he's just going to be like sign f. Right? Simple. The input here is probably in radians. Probably. I can't see that. I can't imagine that would be in degrees. Programmers hate degrees for some reason. I feel like they make way more sense, but for whatever reason, bitches hate degrees. Okay. So we're missing. Oops, the input here needs to come from an existing SSA. Right. That's a pretty good point. So this is going to be SSA is get S input, or else return error invalid reference, which means that here we do sign input. Then here we're going to do the same thing. This should be F here. Like this. Reference. Yo, yo, yo. What's up, what's up? And then here we have B, and then we have A and B here. Most programmers don't have a degree. That's a good joke. I missed that. Even better than radians or turns. Get rid of that 2 pi factor. Dude, if they did turns instead of radians, I'd be all over that shit. For sure. I completely I can think in 0 to 1 very well. Half a circle. Easy. But just like, why are we using, like, surely pi is not a good floating point number, right? Surely. Here we need to, we are going to assume that the input is an F32 if we're using it on both of these. There's a chance that there's not, but, you know, that would be a bug in the compiler, so I'm not really too worried about that. I understand that that could, like, crash our virtual machine, but, like, fuck it, you know? Fuck it! And then we need to add the C bindings to create this thing. So what do we call it? We called it, like, push command fsign and fmol. So push command, and we'll just kind of, like, whoop. I guess we have fsign, which takes in the output ID as well as the input input ID. It's fine, we'll call it this. And then we have fmol, which takes in input A and uint32t, input B. Boom. Chillin'. Chillin', 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 which means that in here, we need to make sure that we store the outputs for both of these. So we just kind of like slap this here and here. And then we should be able, we need to implement these functions somewhere. So this is in shader C bindings. We look for our move for, we've kind of put this adjacent to that, and we're just going to be like, yo, pub export function, this thing, he returns a bool. This thing is going to take in our shader, which I think we have called a shader builder. Let me just alloc infinite bits to represent pi. Exactly. ID U32, input ID U32. Okay. So this is going to be like, let me push some command. Right? We're going to be like, I want to push a command for sure. And I don't really know what's going to be in it right now, but it's probably going to look something like this. We're going to have like catch, return false, return true for error handling. Okay. I don't know what it's pissed about here, but okay, push command. Here we go. So we have F sign is equal to input is equal to input ID, and output is equal to ID. Boom. Okay. Then I guess our fmol is going to look almost exactly the same as this. But this is going to be fmol like this, and we're going to have A ID and B ID. This. Fmol takes A ID, and B is B ID. All right, that compiles, and then does this compile now? He's mad because we forgot to write break. We always forget to write break because why the fuck did we implement switches? It's something where you have to opt in to exiting your switch statement every time. That's like insane, but you know, it is what it is. We've learned since then. And okay, we're running. We're now failing to execute graphics pipeline unknown field. Oh, because we didn't recompile QEMU to run the new options. That's a fair point. He doesn't know how to deserialize our output anymore. And let's see what happens. Root, test, app, dev, TRI, card 1. Let's fucking see it. He aborted because there's unhandled ALU op. Maybe we didn't copy. Maybe the virtual machine did not correctly flush its disk. Okay, there we go. That's better. So now we are crashing at integer part of floating point value out of bounds. That's interesting. Let's take a look at what's going on there. Let's see. Let's run our virtual machine with GDB. Okay. GDB not found. Shut the fuck up. Fine. We will install GDB in this VM or in this environment. Did you envision him as a giant cyborg ducky? I'm sure that made sense to something I said, but I have such low recollection of what I'm talking about at all times that I have no idea what you're saying. Okay. Alright, so this should... Oh, we need to fucking... Oh, I wish that it would flush the disk a little bit better so I don't have to keep re-uploading the same fucking thing. Okay, but here we go. Personifying QEMU. Oh, yeah. I forget that I do that. Okay, so this is vec4 color to U32. Oh, so probably here on rasterization of the triangles, we're probably just assuming that things are vec4s when they're not. We're assuming the fragment shader does output colors. Can we look at this? Okay, so this looks like we've actually successfully run the fragment shader, and triangle rasterization is now falling over. That's kind of my guess here. So can we kind of like claim that that's where we're at now? Fix triangle rasterization. What's going on here? So like, what are we looking at here? Okay, so yeah, this thing thinks he's a vec3, which is kind of surprising. Shouldn't our fragment shader outputs be a vec4? Can we? Okay. So our fragment shader outputs. Oh. Wait, hold on. So we have one output for this fragment shader, which makes sense because we are only running it on a single input right now. And the tag is vec3. But this looks kind of reasonable to me. Maybe not. what is our shader output supposed to be? He's supposed to be some signed value of like sine x, right? And then he's supposed to have alpha of 1.0. So this does seem a little reasonable to me. The fact that this tag is vec3 could be some form of stack corruption caused by it could be that there's a problem with when we assert. Sometimes things on the stack get a little fucked up in my experience. So it might be interesting to be like, can we look at like, do we have a Python shell somewhere? Import math.sine0. No, okay, and then what was our, can we look at like what our vertex shader inputs are? They should be how do you do this? Dereference this and then print it 3 times. So this guy has the correct tag of vec4. That makes sense. Can we confirm if it's hard to confirm that. I wanted to confirm if the frag coordinate output is supposed to be 3 or 4. Maybe it's supposed to be 3. But okay, so we have this as 1. This is one of our outputs. This is another one of our outputs. Okay. And then we have unmarked outputs. I forgot. So these are supposed to be the inputs of our fragment shader, and I think we just didn't get here yesterday, which might explain why things don't make sense. So we have a float 32 output here that is 1 for one of them, 0 for another, and 0 for another. So this makes sense. These are correct. These are the outputs of our vertex shader. So let's make sure that what we are feeding this thing is correct. Okay. So this is going to be like lib.zig, execute, graphics pipeline, our fragment shader inputs. We are feeding it, we are trying to just use this with the third output of our fragment shader. So we're doing sine 1.0 is what's supposed to be happening here. Times 100. Which is what we are getting here. This negative 506, that's what we saw as our fragment shader output. So I think that lines up. Now what does not line up is that the fragment shader output is a vec3, not a vec4. So can we rerun this test? And can we print the fragment shader that QEMU or that Mesa is trying to get us to run to kind of just get a clue for if that's like expected or not? I think that's worth looking at. Test app dev dri card1. Okay, so I did forget to run with ner debug. Those are print vs print fs, and then also we need to re-upload because we keep crashing. God damn it. Okay, so if we crash, we don't get to see the fucking output here. Oh, that's annoying. That's annoying. Yeah, that sucks. But we would get to see it if we ran it in this terminal. I think it's root at localhost env ner debug equal print fs test app dev dri cart1. I think that this is right. Yeah, nice. Okay, so now we can scroll up. So he is supposed to be a vec4 output. It's possible that we made a mistake when we pushed our input definitions. So we do call push output vec4 if it's supposed to be a vec4. And this is on the fragment shader. Do we make that mistake over here? Okay, here we push an output vec4 from here as well. So I'm willing to take a guess that that there might be some stack corruption here. I just want to confirm that before we go farther down this road. So I would like to maybe print out the output here. Just to see. Just in case. Okay. And then I think we probably have to run our copy command again. Okay, so before he crashes, there we go. Okay, we do get a vec4 output. So that's good. So worst case, there's some sort of like stack corruption happening. And now we need to figure out what the fuck is going on. So here, what's happening? He's mad that color 2 p frag outputs marked. This is not the right thing. So the thing we printed was right, but this is just like fucking empty. So what's going on there? Because we printed that we got a vec4 here. So somewhere between when we printed and where this this crashes, we fucked that shit up. But I don't really see how, because we literally just pass it to this. And then immediately start looking at it. So like, what the fuck is going on there? Like, how is that possible? Unless this is called from multiple places? No. Like, hello? That's very confusing, right? Again, we have literally like right before that's called, we print exactly what we'd expect. Okay. And what's the assertion we're getting? Integer part of floating point value out of bounds. Integer part of floating point value out of bounds. I guess if it's very, very slightly off, if it's very, very, very slightly below 0 and we're not rendering that correctly when we print, it could be that we're trying to cast this thing to a U32 and it's not valid. So can we go like color component to U32, and we pass in maybe the shift value. So take in the color, and the shift, returning U32. And we do we do clamp. We clamp the color from 0 to 1. And then we do as U32, int from float, shift left by shift. Okay. Okay. Then this becomes color component to U32. I guess we want to do 255 like this. Which means lets us do color component to U32 like this and like this. Okay, and then that seems kind of reasonable. What's he mad about? Probably need to type return. And probably don't need this as. Oh, we probably do, actually. I lied. I like the little ASCII graph in the doc comments. Oh, down here? Or where did I make a... Did I draw an ASCII graph somewhere? I might have somewhere. I don't know. Okay. He's mad because expected 2 arguments. Right, because we do need to pass in the shift here. So our shifts were 0, 8, 16, 24. Oh, in the clamp function? Right. I did see that. So that was in clamp, like here. Yeah, that's pretty sick. Pretty sick. I love doing those. They're actually like not even much of a like a troll. Like they're very useful. They're not like kind of like this like cute. They're like it's useful to be able to like bang those out for sure. Okay, let's see if that fixes our problem at all. Let's see if that fixes our problem at all. All right. Okay. No, he's still fucking broken. Is it the same spot? Color component 304. Okay. So this is in clamp. He's asserting lower is less than upper. Did I fucking get the argument order wrong and I wasn't paying attention? Oh yeah, it's oops. Oopsies. I checked the docs specifically for that and then just forgot to look. That's pretty funny. Classic. Absolute classic. All right. All right. One more time. That Daft Punk 2005. Wow, I was way off. 98. Way off. My guesses are usually better than that. You were distracted by the graph, maybe? Yeah, probably. Okay, so now we're not crashing anymore. That's good. So it does seem like it was some sort of color clamping thing. And we are still seeing like an RGB triangle, right? Because we're not actually using the fragment shader output. But this is like a big success so far. We have at least run the fragment shader. I don't really know if the colors that we're getting out are right. So what probably makes sense is to try to actually use the colors that come out of the fragment shader as part of our barycentric interpolated values. So how do we do that? Our triangle rasterizer needs to take in our fragment shader and run it for every pixel as we rasterize. We haven't done that yet. This is like a new to us. So I think we can take, instead of taking in the fragment shader outputs here, we should take in the fragment shader itself. Because we can't just like run it once ahead of time like we can for vertex shaders. We have to run it on each fragment shader output. So this thing is going to take in like a fragment shader. So what does that look like? I think we have here a fragment, a shader.shader. Shader.shader. We are running the shader one time, but we have to run it on every single pixel. Yo, what is your keyboard? The sound is so nice, it sounds hollow. What you're hearing is not what it sounds like. There's like a neural network assisted noise gate running on my microphone. And so it's like really changing what you're hearing. What you're hearing, it's like it's just like cherry brown switches in like some like 60% keyboard. But you know, you're not hearing what you think you're hearing. Or I'm not hearing what you're hearing, I should say. Okay, we pass the fragment shader into our rasterizer. That seems reasonable. And this, now we can't compute the color here. We're gonna have to figure that out later. Which means that our rasterizer can't look at the color. That makes sense. And I guess what we're gonna do is we're going to take the inputs to our fragment shader, which we have here, and we're gonna pass those as some of our inputs to rasterization, I guess. So it's probably gonna be like this. Something like this. Something like this. So we have vertex coordinates. We sort them and convert them to pixel coordinates. And then we run this. Okay. Seems reasonable so far. Then here, he's going to not take in colors here, but frag inputs as 3 variables, probably. What is the type of this thing? Shader vec3. This is wrong. This should be shader variable, probably. And this is going to be like this. And these probably have to be, these are optionals, I think. So I have to take the, like, dereference the optional. But we can figure that out, you know, in the future. So now we have some inputs. And we are going to have to interpolate those instead of the colors. So here is kind of like our debug code from yesterday where we calculate the barycentric coordinates of these things incorrectly. Mind, these are incorrectly calculated, assuming that all triangles are flat, which they are not. That was what we were trying to fix today. And we should be able to, I guess, interpolate the inputs to the fragment shader and then run the fragment shader. That's kind of like the right answer here. So frag output is going to be like shader self frag shader. We're gonna like execute this on something like the interpolated inputs. But let's start right now. Can we start right now with just using the first input? This will give us at least something. This is not really, you know, not like the most correct, but it gives us something to work with. It'll at least test if like the rest of the code is working, and then we can kind of do interpolation after. The fragment output, I think surely this is failable. Yep. And we're looking for whatever is marked as the color output. And here is where we did like vec4 to color U32. which means that we can assign the color here. Now, I think we were missing an allocator. So we can just kind of do this, which means that we have to pass an allocator here. Like this, and then presumably if we're allocating something, that means we have to free something. Almost certainly. So here, probably it's like defer frag output dinit or something. What does this execute outputs? No, it just looks like the allocator is used for intermediate state. So we actually don't have to. Hell yeah, dude. All right, does that build? Expected type shader found single shader outputs. That's true. We didn't fix the call site here. So we don't run the fragment shader here. Instead, we run we pass in inputs fragment shader. Does that compile? Here he's mad that he expected a mutable set of variables and he found an immutable set of variables at 201. Yeah, that's fair, I guess. Wait. Wait, why? Frag inputs here is, oh, it's because it's 3 here. So we do, frag inputs mutable. Fuck it. I don't know. Fuck it. Is it like this? So he expected void. Here we need to be able to fail this rasterize triangle function. True. True, true, true. Big true. Okay. Is this failable? Oh my god, it's got to go all the way up. All the way up, baby. All right, that compiles, which means that we should be able to build this thing. And what I expect to see is either like a fully white triangle, probably. Sign 0 is 0. Fully black triangle. I expect to see a fully black triangle. And that would be good. That would mean everything's working and we just have to fucking fix the interpolation of the shader input, which is very doable. Not crashing here is a major, major win for us. Is this running at a fixed frame rate? I think that the test application gets to choose the refresh rate, I believe. And I think that we're just kind of sleeping for like some arbitrary amount of time. I don't remember though. And we're running way slower than whatever frame rate we're trying to run at because of this like print spam. Fully black triangle! Let's go, baby! That's actually so good. Okay, so now we have to like interpolate the floating point inputs this thing, which should be pretty easy. Should be pretty easy. So all we have to do is do like interpolate var, which is going to take in vars, is going to be 3 shader variables, and he's going to return a shader variable. Okay. And what's he's gonna take in like the A, B, and C. How much of each of these things should be used? And maybe this will be a single variable. Now, here we have to take into account which type this is. So if it's an F32, we just return another F32, right? And he's going to be, this does have to take in 3 things. So I guess here we'll assert that v0 dot tag. How do you, can you extract the like enum value from a fucking union in this language? Zig get tag of union. Is that like allowed? How to get the, Sure. No. Is it really not trivial? Maybe there's like a stood meta. Active tag. Yep, that's what I want. So we want stood debug assert that this is equal to this. We want all of these things to have the same tag. If they don't, it's a fucking problem. And I guess asserting here is crazy. We can just fail if it's not true. So if this is not equal to this, or we do the same thing, but with 1 and 2, or 0 and 2, fine, seems reasonable. Return error types not matched. Thank you, two-step. Sorry, I didn't read your answer before I guessed it right, but I appreciate the help either way. Okay, so then we can switch on 0. And we can just do like A times V0 F32 plus B times V1 F32 plus C times V2 F32. Else we can return in unhandled interpolation for now. For now, which means that now wherever the fuck we were here, we can be like frag inputs is just 3 shader variables, so we can say let me think. How is blood so fast at typing? That's so funny. Using blood just like casually, I don't know, it just cracks me up every time. I've practiced a lot. I was into like type race. I was played a lot of like Neopets typing game when I was like 10, and then played a lot of Type Racer like in my life after that. So I've been trying to type fast like since I was a child. You know, you just use all your fingers. Use all your fingers. So I guess we take in the inputs here. So interpolate vars. We take in the frag inputs, and we use what we were previously calling color A, color B, and color C. And we use this as our single input here. So I guess this becomes like something like this. Something like this. I think this won't compile. I think we're close, for sure. He expected this, so I have to try here. Okay, and then he's mad here because I am using a pointer to a constant. So we need to do like frag inputs mute is equal to, I don't know, 1 variable. The types here are all wrong because we're kind of like in this like fucked up prototype mode. So excuse the like nonsensical variable types here. We'll figure it out later. That compiles. That's huge for us. And what happens if we run this? I'm hoping to see a stripy triangle. That's what I'm hoping to see. And I'm hoping to see that that stripy triangle is evenly striped across the whole thing, and it does not kind of start fat and end small like we would hope if it was perspective correct. Okay. Uh, uh. Okay, so that's good. I hope you guys can see that. But that is in fact a stripy as shit, like a uniformly striped triangle, right? So that's really good. That's really good that the fragment shader is now correctly executing and the colors from the fragment shader are correctly being like applied to the triangle. And now we just have to fix the perspective, which is actually relatively easy, I think. So, we were talking about way at the beginning of the stream when we were trying to create our matrix for our perspective matrix. We were talking about how the x and y values that come out of this thing are essentially scaled by 1 over z, right? Because, let's see. Like, as things get farther away from the camera, maybe it's easier to draw it again, right? As things get farther away from the camera, you kind of have, like, in your eyeballs, you know, this width is the same as this width, right? And it turns out that, like, the amount that these things are different kind of scales with the z value, 1 over z. So the question is when we are interpolating a triangle in 2D space, how we have like essentially this triangle, right? Or maybe it's like fuck. Oh god. We have like essentially this triangle. How are we supposed to know, like, if we were to just rasterize this triangle in 2D, the trick here is that you kind of look at the points and you go like boom, 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 go pixel by pixel, right? And these pixels, you're kind of like interpolating. You're at each point, you're taking like the value of stuff at each of these corners and interpolating them according to the area that they take up on the 2D triangle, right? Now, what's fucked up is this is supposed to be like non-linear, right? As you're going like into the page, right, towards this back right vertex, you have to know that like the amount that you're moving is less as you go on. And so my naive way of thinking about this would be, well, we just can't do the interpolation in 2D space, right? You would think that basically you have to like turn this thing so that you see it the way it is as like this like really fucking long triangle. And then you can interpolate in this space. And you could do it that way. But there would, like, the way I would implement this would be basically to just multiply the x and y values by z again. Kind of how wave, right? Because we divided them by z, you could just multiply them back, just not use the like, we have like an output value from our thing as like x as like 4 numbers. We have x, y, z, w, right? And what you're supposed to do is you're supposed to take x, y, z and divide them by w. You could just not do this division, and then everything would kind of work itself out because then the z would be linear. It wouldn't be in this like curve space, and that would work. Now, the problem with that, I believe, is that there's a very hard baked in assumption that you are doing perspective mapping if you do that, right? Which is not always the case. If you're doing orthographic projection, then doing the same thing would still work, but it's not like kind of correct. And it turns out that there's like a generic way of doing this that is always correct for all homogeneous coordinates. And I think I found this by searching perspective, correct barycentric interpolation. I think it was this one or maybe this one. This was the one that explained it best to me. So, we talked a little bit earlier in the stream about homogeneous coordinates, right? You add in this fourth element, the w coordinate, that acts as the divisor for x, y, and z. And what they are doing is they're kind of like explaining in this little piece of paper how to go from barycentric coordinates in the projected space back to like the correct answer in 3D, right? So if your camera's over here, you're looking this way, right? You have this like really warped triangle over here, and you're trying to get to like this unwarped triangle over here. they kind of define this thing as like, how do I say this? A, B, C, and P here are all 3D vectors, as are the prime versions of these, right? So you have on the left your warped as fucked triangle is maybe I don't know which one of these is. Yeah, so your warped triangle, this is the 2D projected one on the left, and this is like the correct one on the right. Your 2D projected one on the left, you have A prime, B prime, and C prime. These are also 3-dimensional vectors. And like we were talking about before, this XYZ over W, XYZ over W, they've represented that here, where they say you multiply A by some matrix that we have, like the perspective matrix, or not the perspective matrix, just literally any fucking matrix. You multiply a 3D vector with a 1 after it by this thing, you end up with an output where you multiply by 1 over Z in our case, and the last element here is 1 over Z. They've inverted this last element, so it's like 1 over instead of the thing, but it's the same fucking thing, right? And so they can say, okay, we have this like definition now where A prime is multiplied by this, and we have like an element over here chilling. Now they can say that if you're trying to do interpolation on the thing on the right or the thing on the left, you're actually going to have like a very similar formula, right? You're either just working in like interpolate like a projected or non-projected space. These are the same fucking formula, right? And it turns out that if you like rewrite this a little bit, right, you can say that like, oh, P prime, we already know that P prime comes from the matrix and P1, right? So they kind of rewrite it this way where you say, oh, P prime is just matrix times P1 for all of these things. Then you can kind of rewrite these things as you have P prime, this, right? You're taking like the 3D components of these things and rewriting your barycentric interpolation. And then they use this like extra piece of information, which is that the divisor, the W component, also has the same interpolation applied to it, right? So you get like several formulas here, and if you just like start shifting stuff around, you can kind of end up where you have the A prime, B prime, the barycentric parameters, the interpolation parameters, in projected space represented as represented by the things in non-projected space, which is fucking huge for us. Absolutely fucking huge. And then it's like the other way around, right? Because we're starting with we're starting with projected space and trying to get back to non-projected space. So they just kind of like shuffle things around. And you end up with this formula here. So to interpolate, and because you look at this and there's nothing in this that says anything about like applying a perspective transform. This is like valid for any homogeneous coordinate, which is like huge. I wouldn't have come up with this myself, because what I would have come up with was like reverse the transformation, just do the other version, right? Just do this instead of doing this. But you can just do the projected version, and then like work your way back, which is so sick. So all we have to do is essentially multiply the value by the Z component, right? Because this hand wavy, how do we say this? This W component is essentially 1 over Z in our scenario. So this is basically saying multiply your projection component, your interpolation thing by Z, and then divide it by all of them added together multiplied by Z. Hand wavy, which is sick. So I think we can just implement that. I think it should be easy. So we have these, and I think that we're gonna call these like Bary projected A, Bary projected B, and Bary projected C. Then that's A prime, B prime, and gamma prime in this world. So we need to take this and divide it by WA, or in our case, multiply it by W, right? Because their W is inverted from ours, right? Their W here is a multiplier where ours is a divisor. So we should be able to go like Bary projected A times sorted triangle W. Now, I think that our sorted triangle is coming in pixel coordinates, and our pixel coordinates are just two U32s. So I think we need to update this pixel coordinate. And we can still stash its X as a U32, and its Y as a U32, but where we will store its Z as a float, and its W as a float as well. The reason that we have U32s for pixel coordinates is that we can like iterate them nicely in two-dimensional space. So where is this used? Norm to pixel coordinate. And norm to pixel coord comes from the homogeneous toward to vec3. So I think we have to fold these three things down now. I think that we can't go homogeneous to vec3. We have to go homogeneous just straight to pixel coord. I think. So here we're going to take the chord as a vec4. We have X, Y, and Z, right? And then we have W is just chord 3. These are going to be in normalized space, I guess. And then here we just do X equals this, Y is equal to this. This is X norm, Y norm. And then our Z is going to be Z norm, and the W is going to be W norm. Simple. Straightforward for us. So this is just homogeneous to pixel coord. Cool. This goes away because nobody's using that anymore. This should be camel case, I forgot. Oops. Okay. And then presumably usages of these things will fall the fuck over. Hold on. I just want to get compiling again. Really quick. So this is Berry projected A. Oh my god. Berry projected B. Berry projected C. This is wrong, but it's fine. We'll come back to this in a second. Berry projected. Oh my god. C. Okay. We have a redeclaration of pixel coord. That's true. Okay, and then pixel coord does not support indexing here. So this is start y, this is end.y. Then we have usages here of x, x, y, 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 x, x. Okay. Okay, 190, he's mad at... We have x and y here, but we are missing z and w. So where do these come from? We're interpolating x and y, which means that the z value is what here? The z value is an interpolated value based off of the barycentric coordinate of the inputs. So we need to interpolate these. So we need to do like... do we even need the z value? What are we trying to get here? we are trying to get here, right? So we actually don't need the z value. We only need the w value. So let's just do this. Yeah. Yep. We don't need the w value here. Or the z value. And then the w value is going to... We don't even really need that either here. So we're kind of like overriding our types here, but we're kind of like... How am I saying this? Like name... We have like... This type is being used in multiple contexts, which isn't really great. W is undefined indicates that this shouldn't be a pixel chord or something. We'll figure it out later. So we calculate the projected barycentric coordinates, and then we just say Bary A is the projected A divided by sorted triangle 0.w. Yep. Divided by Bary denominator. So this is A prime over WA. We'll call this like, we need like a name for this thing. This like A over WA. Bary A. We need like some word for like intermediate. Okay. So now we have A, B, and C. Okay. Now we can do Bary denominator is Bary A inter plus B inter plus C inter, right? And then we just do Bary A is the intermediate value over the denominator. And we can do this for A, B, and C. Okay. Which means that now we can interpolate the variables with Bary A, B, and C. Okay. And maybe that's it, right? It seems possible. 295. This thing's mad because anything that was indexing a 0 now uses a named thing instead. Which is fair. We forgot to delete the Z attachment to this. Okay. Then pixel chord indexing at 325. So this is Y here when we're sorting pixel values. And let's see what happens. Let's see what happens. It would be sick if this worked. Would be sick. Okay, let's fucking... Oh, you tell me that's not fucking working. Look at that. It's like fat at the beginning, skinny at the end. Oh, it's fucking sick. That is fucking sick, dude. We can probably... I think that probably what makes sense is like trying to compare it, but we can't really compare it to the real GPU working because the real GPU is like cutting stuff off. But I'm like fairly confident that that's right. Fairly confident. We gotta figure out why we're fucking crashing for sure. But if we just look real close really fast, let's try to get a little test card one. Let's try to grab a screenshot of that while it's happening so we can inspect it a little bit more closely. Okay, save. Let's try to, I don't know, Dolphin. It's the file manager. Where are we gonna go? We're gonna go to like our pictures somewhere, and presumably we just took a screenshot. Yeah. Yeah, that's pretty sick. Look, you can definitely see that these black lines are getting skinnier and skinnier and skinnier as they get farther and farther and farther into the output. So that's pretty fucking sick. Z will be used for Z-buffer later, right? Probably. I don't know. Presumably we are going to have to do something with the Z-buffer, but I don't know what yet. I haven't really made it that far. But that's pretty sick. That is pretty sick. Cool. I'm really happy with that. We got a lot done today. I mean, it's funny because what I like my thought for what the stream was barycentric coordinate interpolation with perspective correction. I thought that's what we were doing. We spent really more like an hour and 45 minutes on like setting up a test case and 15 minutes on actually implementing the fix, which I guess is just how software goes sometimes. But I'm really happy with where that ended up, which is very cool. Very cool. Yeah, we did like, what do? We set up a shader that does like a sine x along the we can call this like object z axis, I guess. We updated our shader compilation stuff to support sending floats between vertex and fragment shader. We updated our shader compilation stuff to now support multiplication and sine, which is pretty fucking big for us, which allows us to set up this test case. We fixed our rasterization pipeline to actually run the fragment shader for every pixel. And then we implemented perspective corrected barycentric coordinates, which makes this work. So pretty big day. Almost 2 hours on the dot, 2 hours and 5 minutes. So pretty happy with that. I'm gonna call it there. Thank you for watching, guys. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. Today was a little bit unique in that we skipped the 12:30 to 2 segment, which we call happy hour, and we only did the 2 to 4 segment, which is like the mainstream. The difference between the two is that in happy hour, we take the chunk of garbage code that we wrote today and we try to turn it into something that's like committable so I don't feel ashamed when I look back at it. Or maybe we do like some reading on like you know, how to do things that we're a little bit unsure about. Like one of our recent like research streams was trying to figure out physically what happens when you do DMA from a PCI device. So that's what's available. Everything is archived on YouTube. So if you click on the YouTube link in the Twitch description, there are playlists for each project that we're working on. 12:30 to 2 segment is maybe unfortunately for some people, fortunately for me, paywalled because I think that trying to stream more than like give more than 2 hours of VOD a day kind of like makes the VOD worse. So we kind of have like the YouTube segment, and then if you want to see more, you can check out the happy hour segments, and those are available on YouTube member or Patreon. But if you just want to see, you know, the actual implementation of cool stuff, that's all available for free. What else? If you're watching on YouTube, maybe swing by on Twitch if you're online between 12:30 and 4 Pacific time. Say hello. And I think that's it. I think that's the usual plug. Oh, I guess a GitHub link in the Twitch description if you want to see code for this. This will end up under the GPU testing environment repo after we do a little bit of cleanup, for sure. We should be back tomorrow. I think my plan for tomorrow is to try to implement some form of texturing, and if we get through that, then we can try to like try to draw like a full 3D scene, which would be pretty cool. I guess like texturing and matrix multiplication are kind of the two next things to handle, right? Because we want to be able to upload that projection matrix to the GPU and like alter it according to whatever we're trying to show. So we're pretty close, I think, to being able to do real 3D rendering, which is pretty exciting. So swing back by if you want to see more. If not, no sweat. YouTube, goodbye, and Twitch, let's find someone to raid.